I'd like to talk about visual representation of the normal distribution, the bell curve. We see the bell curve everywhere. The expectation is that we know what it really means. But do we? The bell curve, the normal distribution, represents the pattern in which random occurrences in nature show up. Human height, for instance, is distributed according to the bell curve. The average height for men in Ukraine is just about my height, 175 centimeters. A man of 182 centimeters is one standard deviation above the average. That puts him in the top 17%. At 190, he's two standard deviations above the average, top 2.5%. At 198, he's 1 in 1,000. And the tallest man who has ever been recorded was 2 meters 72 tall, a bit over a time and a half my height. Lots of other measurable attributes are distributed more or less according to the bell curve. Human weight, the ratio of height to weight. Skin color, reaction time, and personality traits such as altruism, all can be described by the bell curve. Now, the purest example of the bell curve exists in nature. The rate at which atoms of a radioactive isotope decay, known as the half-life, is a well-known constant. But when any individual atom will decay is totally random. If you count the number of neutrons thrown off by decay in 1-second intervals throughout the day, you'll find that they follow a normal distribution. Now, the normal curve follows a formula developed by Carl Friedrich Gauss over 200 years ago. This looks a little bit off-putting. It involves two constants, pi, that's the radius of the circumference of a circle, and e, the base of natural logs, and two statistics from a population, that is, the average measurement, that's easy to understand, and the standard deviation, which is how far on the average things are from that mean. Generally speaking, one standard deviation is the area from the mean on both sides, encompassing 2/3 of the observations. You don't have to understand it. Excel has functions that'll do the normal distribution for you. Now, the binomial expansion is a lot easier to understand than Gauss's formula, and it works out to about the same thing. If you toss a coin n times, there are 2 to the n possible outcomes. Now, it involves factorials. That's what the exclamation marks are in the formula. A factorial is the product of an integer by all lower integers. It sounds complex, but it's pretty simple. For instance, 4 factorial is 4 times 3 times 2 times 1, 24. So let's go to flipping a coin. That's the binomial function. If you flip it once, you get 2 outcomes. That's 2 to the first power, or 2. If you flip it twice, you get 4 possible outcomes. 2 tails, a quarter of the time. 1 head and 1 tail, or 1 tail and 1 head, that's 2 times. And 2 heads, that's 1. 1, 2, and 1, that makes 4. Flip the coin 3 times, you get 8 combinations. All tails will be 1 time an 8. 1/2 times 1/2 times 1/2. 1 tail and 2 heads will be 3 out of the 8. 2 tails and 1 head will be 3 times out of the 8. And all 3 heads will be 1 time out of 8. You add them up, that's everything. So let's look at it graphically. Now, the bell curve is symmetrical. Both sides are the same. We really only need to look at one side. So I'll slide this over. Graphically, here's what happens if we have 2 flips of a coin, which we just saw. 1, 2, 1. It looks a little bit like a normal distribution. 3 flips looks a bit more, 1, 3, 3, 1. 5 flips, a bit more, and you see that it starts to bend. You get some knees in it, more pronounced at 7 flips. By the time we get to 10, this looks like a bell curve. 20, really close. 40, we're almost there. And 100 flips of a coin is what the red line shows. And that is just about exactly the bell curve. Now, there are other ways to portray the bell curve. It looked from that last diagram as if there might be some observations way out there in the curves at 100 flips of the coin. A scatter diagram is more representative of what happens out toward the tails. This diagram shows 10,000 dots, and you'll notice 95% of them are in the center, between plus and minus 2 standard deviations. That's what the tall part of the bell curve also represents. In this particular diagram, there weren't any observations more than 4 standard deviations from the median of 0. That would only happen about 1 time in 3, so I need 3 charts. I need a chart that went out a little bit past 4, 1 time in 3, to accommodate numbers a little bit beyond 4. And 1 time in 175 or so, I'd need a graph that went out past 5. And you'd get kind of bored looking at that many charts. 1 time in 50,000, you'd need a graph going past 6. I guarantee you'd be bored. And 1 time in 40 million, you'd need a single chart going past 7. But that's more than the whole population of Earth. So my point is that the bell curve only looks flat. It looks like the chances are the same all the way out to the tail, but this is absolutely not the case. What I'm showing here is a graph of 100 flips of a coin. Now the chances of throwing all 100 heads is 1/quintillionth the chance of throwing 70 heads and 30 tails, but they both look the same on the graph, the flat part. Here's another point about IQ. The distribution of IQ is a human construct that is mapped to the bell curve. In other words, instead of giving intelligence tests by some invariant measure, such as a yardstick, to a large population and noticing that it fits the bell curve, psychometricians simply impose the bell curve on their findings to come up with the definition of IQ. Let's try that again. Instead of measuring and discovering that 5/6 of the population are below 1 standard deviation from the mean, they invent a measure and they define 1 standard deviation of the mean as that place which is above 5/6 of the population. They do it backwards, and they did it throughout the whole distribution of intelligence. That's how they standardize their tests. Now, how thin is the tail? Well, IQ is something we can all relate to. I'd like to make a couple of points about it. First of all, the incidence of IQ of people at an given intelligence level falls off rapidly as you go up the scale. Whereas 1 person in 119 and 1 person in 10 has an IQ of 119 or more, it's only 1 person in 1,000 by the time you get to 146. When you get to 164, it's 1 in 100,000. You get to 178, it's 1 in 10 million. And when you get to 190, it's 1 in a billion. That's my first point. It gets rare as you go up. The second point is that these numbers above, say, 170 are speculative. They simply cannot calibrate IQ tests at those levels because there aren't enough people to measure. And those people have better things to do, such as run Microsoft, run Amazon, or invent the internet or something like that. So you may hear speculation that Einstein or Newton or somebody had an IQ over 200. You can be sure that it's only speculation. The second point I want to make is that the original intelligence researchers more than a century ago were either very lucky or they had better intuition than they realized. Up until 10 years ago, the supposition was that researchers would eventually find a handful of genes that were responsible for intelligence. It's much more than a handful. They found literally hundreds, each of which make a tiny contribution to intelligence. So the model of flipping coins is more apt than they realized. It's like the smartest among us got lucky. The way their genes combined in hundreds of flips of the coin came up with many more heads than tails. So let me conclude. The bell curve is universal. It applies to much more than just intelligence. In fact, it comes from a realm where it can be measured accurately, which is not the case in intelligence. It was artificially applied to intelligence, but by luck it fits pretty well. Bell curves are extremely low out in the tails, a fact which the bell curve doesn't show, but scatter charts do show pretty well. And lastly, IQ over 160 is not worth discussing. There are not enough subjects to validate the tests. So that's my short disquisition on the bell curve. Hope you enjoyed it.